All right, so now we're going to move on to another kind of two-sample comparison test, only now this is the two-sample proportion comparison test, okay? Now the two-sample proportion comparison test is very similar to the two-sample mean comparison test, very similar, except we're going to replace the mu with a p for proportion. So this is mean, and this is proportion. So since this is a proportion test, we're going to use proportion, not mean. And we're going to replace the sample mean with the sample proportion. Another difference is that though the two-sample mean comparison, that was a t-test, this one is going to be a z-test. And we've done z-tests before. Remember, we do a z-test with the normal distribution. So instead of using student's t-distribution, this one's going to be a z-test and we're going to use the normal distribution. And so we're not going to need degrees of freedom. So in this one, we will not need degrees of freedom. Another difference is we're only going to do a right tail test and a two tail test. We're not going to include a left tail test. And we could have done this with the mean comparison test, but basically what you have to do is if you have a left tail test, all you have to do is switch the two proportions around, and it turns it into a right tail test. So since that's so easy to do with proportion tests, we're only going to do it with a right tail test and a two tail test. And then the last thing I want to say before we get started is that the formulas in this one, they are crazy. They're possible, but they're just a little crazy. But here's the really cool thing, that everything in these tests can be done in NumWorks or in Minitab or in almost any other statistical software. We're going to do NumWorks, but all of these formulas can be done in NumWorks. So don't be freaked out by the formulas, just write them down. But if you prefer to do it in NumWorks, you can do that. All right, before we get started on going through the steps, I just want to show you an example of the kinds of one way that you can ask the question. You'll be told that there are independent random samples, two of them. We'll have two populations, right? We'll have population 1 and population 2, okay? And you'll be told that how many observations were made. That's the sample size. This one says each. There were two random samples, each containing 70. So that's actually sample 1, population 1, the sample size, which we call N1, will be 70, and over here population 2, which we'll call N2, the sample size, is also 70. So you'll be told the sample size, how many observations were made. And then it'll say the sample from population 1, it'll tell you how many successes there were. So what we're doing is we're just taking two proportions and comparing them to each other. So a proportion is, the number of successes divided by the total number of observations. So if we do 45 divided by 70, that's a proportion. And then over here, if we do 26 divided by 70, that's a proportion. And so what we're going to do is we're going to compare these two proportions. We're going to compare the 45 over 70 to the 26 over 70. And you can see here, the hypothesis, it says test. The null hypothesis is that the two proportions are equal to each other. Because if they're equal, then one of the first one minus the second one would equal 0. But if you subtract the two and they don't equal 0, then they must be different. So the null hypothesis is that they're the same. The alternative hypothesis is that they're different. And look, it gives us a level of significance. Alpha is 0.06. So we're seeing all the same stuff in a proportion test that we saw in the other kinds of hypothesis tests. So let's go ahead and learn the steps. All right, as usual, step 1 is going to be to state the null and alternative hypotheses, and if it's a right tail test or a two tail test. I just said a couple minutes ago that we're not going to do a left tail test here, okay? The null hypothesis, very simple. P1 is equal to P2. That's typically our, it was the same hypothesis with the mean comparison test. We said mu1 is equal to mu2. Well, this one's P1, the population proportion 1 is equal to the proportion from population 2. And it's the same for the two-tailed test. The null hypothesis is that P1 is equal to P2. That's always going to be the same. But our two different kinds of alternative hypotheses is one of them is that proportion 1 is greater than proportion 2, and the other one is proportion 1 is not equal to proportion 2. And as usual, when we see the not equal to, that it implies a two-tailed test. But when we say that proportion 1 is greater than proportion 2, that is a right tail test. Moving on to step 2. In step 2, again, we're going to identify a bunch of statistics. Here's what we have. We have to identify x1. That's the number of successes. Okay, that's the number of successes in population 1. x2 is the number of successes in population 2. Then we have n1, that's the sample size, that's how many observations, and n2 is also the number of observations, but for population 2. And then here's the alpha. And here's what I want you to know. x1, n1, x2, n2, and alpha are all going to be given to you. All 5 of those pieces of information will always be given to you. So then what about this P1 hat, this P2 hat, and this P star? Well, let's talk about those. Those we're going to have to calculate. So the P1 hat and the P2 hat, those are just proportions. That's, P1 hat, that's the proportion, because P hat is a proportion. It's a proportion from population 1. And then P hat 2 is the proportion from population 2. And it's very simple. We do the number of successes divided by the number of observations, or the number of successes divided by the sample size, right? So we take the number of successes from population 1 divided by the sample from population 1, and that gives us the proportion from population 1. Same thing from P2. But what about this P star? This P star only exists when you have 2 or more proportions. It's called a pooled proportion. Okay, it's a proportion. Proportion. It's a proportion that includes both x1 and x2, and it includes both n1 and n2. It's kind of a combined proportion of P1 hat and P2 hat, because it makes use of x1 and x2, and then n1 and n2. Okay, so let's see what the formula looks like. All right, so you can see this is a pretty easy formula. You just add the 2 successes and divide by the sum of the 2 sample sizes. So sum both successes from both populations, and then sum up both sample sizes in the denominator, and we call this the pooled proportion. Now sometimes this P star goes actually by P hat, which sometimes can be confused with a single sample proportion, but I just want you to know that you may see P hat representing the pooled proportion instead of seeing P star, okay? But for the purposes of this 2 sample proportion comparison, P star is exactly the same thing as P hat. But if you see P hat 1, that's only for the sample from population 1, and if you see P hat 2, that's only from the sample from population 2. And the good news is that NumWorks, if you put this and this and this and this into NumWorks, it'll give you this and this and this. It's very convenient. All right, in step 3, we're going to identify the Z star critical value. Now, you've already done this in the 1 sample hypothesis test, and then you did the T star and the 2 sample mean comparison test. That's all we're doing. We're going to go into NumWorks, we're going to go into the distributions, and we're going to get the Z star critical value. Now, I'm trying to remember, I think it's possible that there's another place in NumWorks where you can get this Z star critical value, and we'll see when we do an example. Remember that it's based on alpha, and it's based on whether you're doing a right tail test or a two-tail test. Because remember, when you do a two-tail test, you have to divide your alpha by 2 when you identify the critical Z value. So here's our notes. For Z critical, we're going to use the normal distribution. we're going to need to put a p-value into the calculator in the far right box. That's our p-value. And remember, the p that we plug in is equal to alpha for a right-tail test, but for a two-tail test, we'll do alpha divided by 2. Now, because we're only doing a right-tail test and a two-tail test, because we're not doing a left-tail test, we, for this test, are only going to use a critical value that is positive. So Z star, our critical value, we're only going to use a positive critical value in this test. Okay, and then we're going to make our statement. We're going to state our Z-score rejection rule, which is going to be reject H sub O if Z, our calculated test statistic, is greater than our critical value Z. And we can put these, maybe I'll put this in quotes so that we see that we're actually writing this out in our hypothesis test. All right, so let's move down and make a little bit more room for step 4. All right, in step 4, we are now ready to calculate the standard error and the Z-test statistic. Now, the formula for the standard error is pretty ugly, and so is the formula for the Z-test statistic, so let's look at them one at a time. Okay, here's our formula for the standard error. So to calculate the standard error, here's what we're going to need. We're going to need P1 hat, which we calculated in step 2. Then this is going to be, I don't know if you recall, it's basically the complement of P1 hat. We do 1 minus P1 hat, which sometimes is referred to as Q1 hat. Okay, but we're just going to call it 1 minus P1 hat. So we're going to take P1 hat, then we're going to multiply it by 1 minus P1 hat. Then we're going to divide it by the sample size from the first population. Then we're going to add the same thing over here, only from population 2. So we take P hat 2 times 1 minus P hat 2 over the sample size from population 2. Okay, so if we do that to both of them, add them together, and then take the square root, that gives us the standard error. Okay, now I know it looks intimidating, but I promise you, if you were to write it down on paper, or if you were to do it in, a scientific or a graphing calculator, it wouldn't be that bad. And now for the formula for our Z-test statistic. Z equals P1 hat minus P2 hat divided by the square root of P star times 1 minus P star times the sum of 1 over the sample size from population 1 plus 1 over the sample size from population 2. That's 1 over N1 plus 1 over N2. Whoa! Exactly. Now, this really isn't that bad. It looks a little overwhelming because we have this radical in the denominator, but really all we have here is the difference of the two proportions. And then if you do this radical thing in the denominator separately by itself, if you do this in a scientific calculator separately by itself and then put it down to 6 decimal places, then all you have to do is do P1 hat minus P2 hat divided by whatever you got from this. But I have really good news for you, because this standard error and this Z are both easily determined in NumWorks if you just put in the initial information that you collected in step 2. So step 2 is really important. If you get all those numbers, that information from step 2, just the X1, the X2, the N1, and the N2, you put that stuff into the NumWorks calculator, and then it'll just give you the standard error, it'll give you the Z, it'll give you the P star, it'll give you the P1 hat, the P2 hat. It gives you basically everything. All right, let's make some room for step 5. Okay, just like in the other hypothesis test, step 5 is identify the p-value and make a decision. Remember, we're going to compare our p-value to the alpha, and then we're going to make a decision based on the p-value and also comparing the Z to the critical Z value. Now, sometimes the Z statistic, this thing right here, can be pretty large. It can be 20, 30, 50. The thing is, most technology applications like the NumWorks calculator and Minitab, they will not give you, if z is too large, they'll just tell you that p is equal to 0 when it is not equal to 0. So here's what I want you to do. If you get a z value that is larger than 4.75, I want you to put in p equals 0.000001. That's 5 zeros and then a 1. You're going to put a decimal and then 5 zeros and then a 1. So if you wind up with z equals 23.4 and they say, what's the p-value? You just put in 0.000001 and it'll accept the answer happily. Another problem with technology is they'll tell you that p is equal to this crazy looking thing. It'll have this e-3 thing on the end. All this e-3 thing means is move the decimal point over 3 places. 1, 2, 3. And then you'll put zeros in the places. So you wind up with 0.00, then the 7, then the 865. See how the decimals between the 7 and the 8, it used to be right here, and then this -3 says move it over 1, 2, 3 digits, and that's why we wind up with it over here. So if you get an answer that looks like this, then just move the decimal point to the left this many places, and then enter that answer as your p-value. And then we're going to make a decision, and you're either going to say do not reject h sub o, and we're going to say that if p is greater than whatever alpha is, or if our z statistic that we get from here is less than our critical z value. The other alternative is we'll say reject h sub o, and we'll do that if your p-value winds up being less than whatever the alpha is, and at the same time that'll mean that your z statistic that you got from here is going to be greater than your critical z value. Then step 6, the last thing we'll do is we will confirm with a confidence interval. And this is how we calculate the confidence interval. We're going to take the difference of P1 hat and P2 hat. It's the same thing that's in the numerator of this. And again, the NumWorks calculator is going to do step 6 for you. You're probably not going to have to do this by hand. But if you did do it by hand, you'd have to take your critical z, multiply it by your standard error, which you got here. Then you take your difference. You're going to subtract, this is our margin of error right here. Take your margin of error, subtract it from this difference. That'll give you a number to put right here. Then take your difference and add your margin of error. That number will go right here. And this is what you put in the middle of the confidence interval. Okay? See what it's saying here is it's saying the difference between the population proportion from population 1 and the population proportion from sample 2. And the null hypothesis says that this is going to be 0. The alternative hypothesis to this says it's not going to be 0, okay? And I'll show you, I think this will make a little more sense when we do an example in the next video.